Hello, this is Teach Nichols, and this lecture is on relativity and light. The essential question is, what is general relativity and what sort of implications does it have for physics or the world around us? So general relativity says that the laws of physics apply in any non-accelerating frame of reference. A frame of reference is basically where you are, what we're measuring things relative to. So when you're standing still, your frame of reference is also standing still, here fixed to the surface of the Earth. That's considered a non-accelerating frame of reference. Other non-accelerating frames of reference, a car, if it's moving at a constant velocity, an airplane, if it's moving at constant velocity. Any of those things could be frames of reference, and the laws of physics seem to apply, right? You can throw and catch a ball from hand to hand when you're standing still. You could do the same thing in an airplane, right? Just because the airplane's moving doesn't mean the ball smacks you in the face when you toss it from hand to hand. You essentially can't tell the plane is moving because it is fixed to your frame. And so if you're inside of the frame of the airplane, all of the standard laws of physics apply. Incidentally, we're not going to talk about non-accelerating frames of reference, but they're really interesting down the road. So if you observe the world from one frame of reference to the other, you're going to end up with some different conclusions about an object's location or velocity, but you still can use Newton's laws of motion and kinematics to do calculations. So for example, if we have a person standing on top of a train throwing a baseball, that person could measure the velocity of the ball, they could calculate how far that ball moves in that time, and that distance would be relative to them. Another person who is watching the person on the train from the sideline could do the same. They're going to come up with a different answer because the velocity of the ball looks like it's a lot faster if you're standing on the side of the train track, because the velocity of the ball is the velocity it's thrown at plus the velocity of the train. So we're gonna note that that ball covers a much bigger distance in the same amount of time, but we still can use the laws of motion and kinematics to do those calculations. Slightly more complicated example, a pilot in an airplane. If you were a pilot in an airplane and you drop something, just like a passenger in an airplane that drops something, you see that thing go straight down, right, from your frame of reference. And so we could use free fall to figure out how far it goes and how fast. But a person standing on the ground watching the thing fall actually doesn't see it go straight down. We see it cover a parabolic arc, and that's because from our frame of reference, that ball has two velocities, a sideways, and then it's going to be accelerating downwards. The ball is, not the frame. And so we would have to use different equations to figure out what that looks like from our frame. But regardless, Newton's laws apply in both scenarios. So these rules about observing things from one frame to the other work for all objects that are moving, except for light. So Einstein realized that light is special. Light is special because no matter what frame of reference you're in, you measure the speed of light to be the same. You measure light to go at 3 times 10 to the 8th meters every second. That is otherwise known as lowercase c, the speed of light, no matter what frame of reference you are in. So in other words, the person standing on the train turns on a flashlight, does a little science experiment, discovers that that light travels at the speed of light, okay, travels at c. Maybe they're bouncing a little piece of laser off of a mirror and then measuring how much time it takes that laser to come back. That's essentially how we found out the speed of light. So that person comes up with an answer for the speed of light. But let's say we've got an observer on the sideline of the train, and they are also measuring how fast is that light that seemed to be traveling on the train. Even though the light source is moving, the person on the sideline still gets the exact same data that the person standing on top of the train does. So this is weird because light does not seem to follow the law of general relativity. Okay, so I'm not going to go into the whys behind Einstein's revelation about the speed of light because there just isn't time. It took Einstein a lot of years to figure that out. But I am going to go into some of the important implications in physics and engineering that come out of this revelation. The first is something known as time dilation. So let's imagine we have a clock. We've made this clock out of a little pulse of light that we're shining out of a laser, and that light goes 150,000 meters to a mirror and bounces off that mirror and comes back to a detector near where the light was launched. Because the speed of light is constant, it is a universal constant, this is a really good clock. The clock essentially ticks once per second, right? We go down and up and then we tick once per second. So if you are holding this clock in a non-accelerating frame of reference, you're always going to see this clock ticking once per second. Whether you are standing still or whether you're in an airplane moving constantly, we're going to see the same thing because light always has the same speed. Now the weirdness arises when the clock is on the airplane and you are standing still, or vice versa. So if the observer is not traveling with the clock, okay, two things have to be true. Number one, speed of light is still exactly 300,000 meters per second. But the distance that light is observed to travel is more than 150,000 meters because it's got to cover the hypotenuse, a longer distance, because we can see it moving through space. If you think about the way relationships and equations work, right, velocity is distance over time. If the velocity is constant and the distance goes up, the only way to do that is for the amount of time it takes to go up as well. So, in other words, the observer that is moving notices that a second takes longer than the person that is not moving. Okay, so the single kind of conclusion bullet point of time dilation is that time actually passes slower when you're in a moving frame of reference. If you look at this animation, you can see those two clocks together, right? So the clock on the top is the one that's standing still or in our frame of reference, and the one on the bottom is the one in the moving frame of reference. And you can see from our perspective, time passes a lot slower for the object that is moving. The faster the frame is, the bigger the effect is, because obviously the more distance it's going to cover. So really fast moving objects, time does not pass nearly as fast in those frames as it does for a frame that is standing still. This is a real effect. We notice this in actual real-world important applications. Like, for example, our GPS satellites that we launch up into space that orbit the Earth really fast. We put these really accurate clocks in them, and when they come back to Earth, they are behind the clocks that have been kept at Earth because time is actually passing slower in the satellites than it does on Earth. There's been a well-known thought experiment about, like, how do you live forever? Like, if you sent an astronaut up on a really, really fast rocket ship, time would travel slower. They would come back and they would not be as old as their twin that stayed on Earth. Interstellar and a couple other movies reference this as well, and that's actually good science. The second implication of general relativity and time's sort of seemingly defiance of it is something known as length contraction. It's a lot harder to come up with a conceptual explanation of why this works. So I'm not going to try. I'm just going to kind of tell you the net results, but I will post a video where they get into it, but it's more like a 20 to 40 minute explanation. So I'm trying to avoid that in this. But the short answer is that objects and space itself that are in moving frames of reference also shrink. The length of objects changes or contracts in the direction of their movement compared to a stationary observer. In the image shown here, you can see if we launch a rocket ship really fast towards this star, Alpha Centauri, if we are on Earth, what we will see is that rocket ship actually is shorter in the direction of movement. It's not thinner, but it's shorter. So if I tried to measure the length of the rocket ship, I would get a different answer if that rocket ship was moving than if that rocket ship was standing still. Now it's interesting because of relativity, like the astronaut in the rocket ship could take those measurements too. And from that person's frame of reference, they're standing still and the Earth and the star are moving past them. Therefore, that astronaut actually sees the Earth shrunken in the direction of its motion, the star shrunken in the direction of its motion, and in fact, the entire space in between the Earth and the star are shrunken based on relativity. Of course, the faster the spaceship, the same thing, the bigger this effect is. And this is kind of a cool thing because that means that if the space is shrinking, we actually don't have to go as far to get from Earth to the star, the faster we move. This is a real effect as well. You have to be moving really fast. On Earth, one of the only things that we can accelerate up towards the speed of light are particles and particle accelerators. But they have found that the length of the particle accelerator actually changes based on how fast the particles that are moving in them. So the distance those particles have to travel is different depending on how fast they are. The last implication is something called Doppler Redshift. And you may have talked about this a little bit in your 9th grade physics class, but anytime you have a wave, like light or sound, that is being made by a moving source or has a moving observer, the speed of that wave is constant, but what is not constant because of the wave equation is the observed frequency and the wavelength of that wave. So if you are making a wave and moving to the right, that wave gets squished together in front. The frequency of the wave is higher, the wavelength is lower, and in the space behind the moving object creating the wave, you'll notice the wave actually gets stretched out. If you were traveling along with the wave, you would notice a constant frequency, whatever the frequency of the wave source is. In terms of light, since the frequency and the wavelength tell you what color the light is, you actually notice objects being different colors based on what direction they're moving. Objects that are approaching you appear bluer than they should, and objects that are retreating away from you appear redder than they should. This is a really big deal in the world of astronomy because we can use this to look at distance objects in space and figure out A, which way are they moving, and B, how fast are they moving relative to us based on how big this redshift is. One of the very first mind-blowing moments that used this application had to do with looking at all of the stars and galaxies in the universe and realizing that all of them were red. Everything in the universe is redder than it should be. And what that means is that everything in the universe is getting further apart. Now, that doesn't seem that crazy. I mean, it kind of seems a little bit crazy, but the thing that is big deal about that is that that means if you turn time backwards, things were closer. And if you keep turning time back, eventually everything existed at a single point. So the Doppler redshift of the universe is our direct evidence that the Big Bang happened, and it can also tell us, roughly speaking, when it was. All right, done with this video. Take a few minutes and revisit the essential question: what is general relativity and what implications does it have? And do you have any other questions or noticings or wonderings that come up on this topic that you could jot down in your notes? Thanks for watching. Enjoy the comic, and I'll see you guys in class.